All right, to kick off our pandemic version, we are going to be focusing on Unit 1, which will go over limits, a topic from pre-calculus, the intermediate value theorem, which I believe you talked about in pre-calculus, the definition of continuity and what it means for a function to be continuous, and then we'll do a big look at the concept of local linearity, which will be new in understanding a derivative. In your packet, you have a list of objectives. These are all the ones for Unit 1. For today, we're going to talk about being able to describe what a limit is and also being able to solve a limit. I'm going to go over that process with you, but the next video will take you through some more specific examples. Okay, so what is a limit? A limit is going to be the intended height. So that's going to be a y value, an output, a range of a function. My stylus is not very good. I apologize. My one from school died and I had to use this other one from home. Hopefully I'll up my game soon. So a function, we'll call that function f of x, has a limit at a point c if the limit, I'm going to change colors and you'll see why in just a second. If the limit as x approaches c from the left, that's how we read that, of that function is equal to the limit as x approaches c from the right, so positive bigger values coming in from the right of that function, which basically means the path coming in from the left is pointing to the same height as the path coming in from the right. So a non-mathy version of what a limit is. The path approaching C from the left meets the path approaching C from the right. Notice I don't care what's going on at C. I care about what's going on near C or around C. So in this case, our C value, I'm going to say that C is equal to 2. So if I were to take the limit as x goes to 2 from the left, so my path leading to 2, my function height from the left, has an intention of landing at 4. Then I'm going to think about the limit as x goes to 2 from the right of my function. So my path as x gets closer to 2, where are my y values going? They are going to 4, which means that overall the limit as x goes to 2 of my function is equal to 4, because blue and red make purple. Now again, doesn't matter that there's a big pothole here at 2, okay? Doesn't matter that we never actually get to the height of 4. It's about the intention, right? I am intending to end at 4 from the left and 4 from the right. My path approaching from the left is meeting up with my path that's approaching from the right. What I actually do when I get to 2 looks like I'm going to take a hop, skip, and a jump, and that's fine, but the limit exists, and the limit is equal to 4. Limits can be found in 3 general ways, which you might remember from your previous math classes. The first way is using direct substitution. The second way is using a graph. And the third way is using a table. So direct substitution means that if I'm taking the limit as x goes to 2 of a function, well, I'm just going to plug in 2. and see what happens. When I plug in 2, if I get a number, cool, that's my limit. If I get a fraction, great, that's my limit. If I get 0, also great, that's my limit. If I get 0 divided by a number in the denominator that's not 0, great, that's my limit. These are all ways that direct substitution is just beautiful. Plug it in, you're done. But then there's some times where we get some weird things from direct substitution. So maybe I had a fraction, but that fraction has a number in the numerator and a 0 in the denominator. We would then say that this limit is undefined. Because do we know what it means to divide by 0? No, we don't. So we would say that this is undefined. You could write that as DNE, the limit does not exist, Mean Girls style. But then we could describe the behavior. The thing is, if we divide by 0 on a graph, we would see a vertical asymptote, which means that our function is either going to go up to infinity or down to negative infinity. I will tell you that all of these are ways to answer a limit question if direct substitution leads to a number over 0. You can say the limit is undefined. You can say the limit does not exist. You can say, I'm going to actually change that. We're going to say that this is undefined. Ignore me. You can say that the limit does not exist, or you can describe the limit as going to positive or negative infinity. I'm going to stay away from that word undefined. For those of you that have had math analysis, you understand why, hopefully. Okay, so there's the last situation. And the last situation is the fun one. That is where you get 0 over 0. What? 0 over a number up here, well, that's just equal to 0, so that's your limit. A number over 0, we just found out that does not exist. 0 over 0, mind blown. This is what we call an indeterminate form. Now, little hint, 0 over 0 means you found a hole in the graph. And just like that last one where we had a big pothole on our function, the limit still existed. So this limit will exist. We just have to do a little bit more math to figure it out. And that's what the next video will focus on, is how do you do that extra math? How do you keep going when you get 0 over 0 to find that limit? Okay, so 0 over 0, keep going. 0 over 0, keep going. I like to think about it like Dory swimming. 0 over 0, just keep swimming, just keep swimming. You're gonna keep going, okay? Couple little side notes about this whole graph concept. Mr. Lakin will mention this in another video too. If the graph is given, cool, use it. Like that last one, we just used the graph, right? If you have to graph it on your calculator, you gotta be careful because your calculator doesn't always show the things that you like. If you yourself are drawing a graph based on information, ready for it, wait for it, that's sketchy. Don't do it, okay? You can draw it for your own knowledge, but I wouldn't rely on it unless you are accurately plotting points that you know are specifically drawn correctly, okay? Because sometimes we have a tendency to just kind of like haphazardly draw things, and what we see might not really be what's going on. Our table is our least efficient way to do this, because if you think about subbing in values from the left and then values from the right, it's not possible to actually get really close, because even if, let's say we were finding that limit as x goes to 2, and you plug in 1.999999999 and 2.000000001, okay? You're still really far away from 2 because of weird how numbers work, right? There's an infinite number of numbers between any two numbers, and then your head just starts to hurt. And so this will always be your kind of order of operations. You always want to start with direct substitution for a limit. Sub it in, see what happens. You might have any of these results that you're going to have to deal with. If the royal they, provide you with a graph, use it. If you graph it on your calculator, meh. And if you draw it, it's sketchy. Be careful with how you're answering. And then this table version is like a little bit sad. Helps us understand coming from the left and coming from the right, but we got to be really careful about how reliable it is when we start actually applying it. All right, so that being said, we're going to work on some group work that goes into figuring out, again, what is a limit and looking at a rational function, a ratio function, and working on this process.